What if you could hold the future of electronics in the palm of your hand? And what if that future was much smaller than you could ever imagine? Picture a world where electronic components are no larger than a single molecule. This isn't science fiction. It's the emerging field of molecular electronics. A branch of nanotechnology, molecular electronics, explores the use of molecular building blocks to create electronic components, promising unprecedented size reduction benefits. Welcome to the fascinating world of molecular electronics, where the future of electronics is not just small, it's molecular. The seeds of molecular electronics were planted back in 1956, and the first major breakthrough came in 1974. Just like a seedling that grows into a mighty tree, the field of molecular electronics sprouted from the fertile ground of scientific curiosity and innovation. This field, which explores the use of molecular building blocks to create electronic components, was nothing more than a concept in the mid-20th century. It was an idea that held the promise of size reduction benefits, of miniaturizing electrical circuits to a scale never before imagined. In 1974, two brilliant minds, Aviram and Ratner, proposed the concept of single-molecule electronics. This branch of nanotechnology aimed to use single molecules as electronic components, an idea as revolutionary as it was challenging. Imagine using a single molecule, something so tiny it's impossible to see with the naked eye, as a working part of an electrical circuit. But the path to progress is often riddled with obstacles. Establishing reproducible electrical contacts and conducting measurements at cryogenic temperatures were among the challenges faced in single-molecule electronics. Yet, these challenges did not halt the progress. Instead, they fueled the quest for solutions, leading to the development of conductive polymers. These polymers, like polyacetylene and polypyrrole, offered high electrical conductivity. They could be fine-tuned through organic synthesis methods, opening up a world of possibilities. Despite their advantages, conducting polymers faced their own set of challenges in processability and large-scale applications. Despite the challenges faced in the early years, the field of molecular electronics continued to grow, leading to the development of conductive polymers. The dawn of molecular electronics had begun, and its light promised to illuminate the path to a future where the boundary between the physical and digital world blurred even further. Fast forward to today, molecular electronics has the potential to revolutionize various industries. Imagine a world where electronic devices are smaller, more efficient, and significantly more powerful. This isn't a far-off dream, but a reality that molecular electronics is ushering in. At the core of molecular electronics is the concept of using molecular building blocks to create electronic components. This innovative approach offers potential size reduction benefits, a game-changing factor in our ever-shrinking digital world. But it's not just about making things smaller. Molecular electronics could also lead to devices being more energy efficient. With the looming climate crisis and the urgent need for sustainable solutions, this aspect of molecular electronics is particularly exciting. However, just as with any pioneering technology, molecular electronics also faces its set of challenges. One of the key hurdles is establishing reproducible electrical contacts. In simpler terms, we need to ensure that the tiny molecular components can consistently and reliably connect with each other to form functional circuits. Another challenge is the need for conducting measurements at cryogenic temperatures. Cryogenic temperatures are extremely low temperatures, often hundreds of degrees below zero. Working under such conditions can be technically challenging and resource-intensive. But let's not forget that every technological advancement, from the invention of the wheel to the development of artificial intelligence, has been met with challenges. Overcoming these challenges is what propels us forward, opening doors to new possibilities and innovations. Molecular electronics is no exception. Its potential to transform our digital world, to make our devices more compact and energy efficient, is a promise that is impossible to ignore. The journey might be filled with obstacles, but the destination is worth every step. While challenges remain, the promise of molecular electronics is too great to ignore. So what does the future hold for molecular electronics? A question that invites us to envision a world where the electronics industry and our lives in general could be reshaped. With the strides being made in nanotechnology, molecular electronics is no longer a distant dream, but an emerging reality. Imagine having electronic components that are not just miniaturized, but molecular in size. This isn't just about shrinking things down, it's about creating a new paradigm of how we build and use technology. From more powerful, energy-efficient devices to potentially revolutionizing fields like healthcare, material science, and climate modeling, the possibilities are astounding. Yet, as with any emerging field, challenges lie ahead. Establishing reproducible electrical contacts and conducting measurements at cryogenic temperatures are just a few of the hurdles to be overcome. But every challenge presents an opportunity for innovation and discovery. By staying informed and engaged with the developments in this field, we can all be a part of this exciting journey toward a molecular future. As we continue to push the boundaries of what is possible, one thing is certain: the future of electronics is not just small, it's molecular.